talk about question 5 here. Part A says use the data in the table to approximate Ben's acceleration, and you have data in the table that refers to actual position and also actual velocity. So if we were to approximate acceleration, we would most definitely want to take the derivative of the velocity, which would be v of 10 minus v of 0 all over 10 minus 0. Are you kind of seeing a common theme here, everybody? I hope you're starting to see that a lot of times this first one is just a difference quotient, and then when you take v of 10 minus v of 0, you get 0.3 divided by 10, and then when you simplify that, you get 0.03 meters per second square. You see you get an answer point right there, okay? You'll see where the units of measure kind of come in here towards the end. Part B says, using correct units, interpret the meaning of the integral from 0 to 60 of the absolute value of v of t dt in the context of this problem. I really want to make sure that we are clear on that absolute value idea. Remember that the integral from 0 to 60 of v of t is simply your displacement. Please understand that. That is just your displacement over the 60 seconds. As soon as you add absolute value symbols around it, it's not displacement anymore, it's total distance. I spelled that wrong. Total distance over the interval from 0 to 60. So displacement versus total distance is different if you've changed position, or changed direction, rather. And then, so what you need to make sure is that you realize that you put that word total in there. It's the total distance. It's not the change in position. It's the total distance in meters that Ben rides over that 60-second interval from 0 to 60. And then you are asked to actually evaluate that sum using a left Riemann sum with the indications, or with the data here in the table. So again, you have different subintervals, so you need to make sure that you're taking your difference of 10 times, use this lower guy down here, so 10 times 2 plus 30, that's your difference here, times 2.3, and then 20 times your 2.5, okay? 2 times 10 is 20, 2.3 times 30 is going to give you 69, and then 2.5 times 20 is going to give you 50, and so when you add those together, you'll get 139, and then put meters there. So you get a point here for the meaning of your integral, understanding that and articulating that, and then also the approximation being 139. Part C here says, over 40 to 60, must there be a time when his velocity is equal to 2? And I know that equal to 2 thing seems kind of odd, like that just kind of seems random. And why are they throwing that in there? Think mean value theorem, everybody, okay? Mean value theorem. Remember we talk about the fact that your if your average speed is a certain value, then if you have a twice differentiable function, meaning it's continuous and differentiable, then there's going to be some place within that span of time where your derivative or your instantaneous rate of change is equal to the average rate of change. So go through and think, okay, if this just seems kind of random out here, this random 2, let's see what is actually happening in terms of the average. Maybe it's going to work out to be 2. So I'm going to take b of 60 minus b of 40 all over 60 minus 40, and this should be recognized to you as the average velocity, your change in position divided by your change in time. When you get those values of 49 minus 9 all over 20, you do in fact get 2, which tells you that your average velocity is 2 meters per second. So therefore there has to be a time between 40 and 60 where your velocity is in fact equal to 2, your instantaneous velocity. You don't have to go through and explain the mean value theorem. You don't have to go through and make sure that it meets or explain that it meets the hypothesis of the mean value theorem of being continuous and differentiable. You just have to say the mean value theorem implies. Your work here already justifies that you know what the mean value theorem means. So don't re-explain anything. You don't have time. Just put your difference quotient down and then tell them that it's because of the mean value theorem that we can say this. Okay? And then part D. part D kind of seemed really, really, really yucky, but to be honest, it wasn't terrible. I mean, it wasn't beautiful or anything. You might have groaned a little bit when you first saw it. But it's saying that we have this light, and Ben rides so that the distance L of t is the function we're talking about. That L of t function is the distance between Ben and this light. And it satisfies basically the Pythagorean theorem. At what rate is the distance between Ben and the light changing? So if you want to think about what this question is asking you, it's asking you what is the rate um, what is the rate of the distance between Ben and the light changing at 40 seconds? This is what we're trying to find, okay? This is the function they gave us. So we obviously need to do something with his derivative. Now, if I am trying to find his derivative, I'm going to pull my 2 to the front, leave that alone, and then chain on the derivative of that function because it's with respect to time. So we have 2 times L of t times L prime of t. Then the derivative of 12 squared is just going to be 0 because it's a constant. And then you have the same idea here with your b of t function. So you have 2 times b of t chaining on the derivative of b. Okay? And now I'm dealing with all of this stuff at 40, but this guy right here is what I'm solving for. Okay? So I'm going to go ahead and plug in 40s wherever I see it. So I need 2 times L of 40 times L prime of 40, that's what we're not going to know, is equal to 2 times, well, b of 40 I can get from this table up here, and I have it wrote down. I'm not going to take the time to go up there and grab it. B of 40 was 9, and then b prime of 40 would be your velocity at 40 seconds, which was 2.5. And I'm going to go through and evaluate this. L of 40 I can get by putting back into this equation. So L of 40 squared is going to equal 144 plus b of 40, and we said that b of 40 was 9, right? So we have 9 squared here. 144 plus 81 is 225. And so when I square root that, to get that, I'll get 15. So I know that L of 40 is 15. And so that will go here. So I have 2 times 15 times L prime of 40, right? We don't know that, is equal to 2 and 2.5 make 5. 5 times 9 is 45. And when I divide off, this is 30. 45 over 30 is 3 halves. And so we have this 3 halves meter per second. Okay? You don't have to do anything to justify other than just show your work. There's no statement that needs to be stated there. So let's talk about how we got our points. In the first part, you got your point just for having the 0.03, or even this 0.3 over 10. That would suffice. And then the second part here, you got if you interpreted your meaning correctly, and then also if you got the correct approximation of 139. Okay. Part 2, you had to show your work here. That will get you the difference quotient point, and then your conclusion. And you may make sure that you say mean value theorem in that conclusion. Okay. And then the correct derivatives. So you had to make sure you had that L prime of t chained on there and b prime of t chained on. You had to use b of t to get your b prime of t. That just got you a point. If you realized that b prime of t was 2.5, great. And then you got a point for your answer being 3 halves. And then your last point, notice these all add up to 8. Your ninth point would be if you had the correct units in either A or B. So if you got the point, if you got in either space the correct units, you get a point. So you could have been wrong in one of them and still got a point. Okay? Alright, so that was question 5. Let's scroll down here to question 6 and look at this guy. Okay? This one I thought was actually a little bit more difficult. The reason being is because they gave you this function for g, but they told you that f was defined as g minus cosine of x over 2. Okay? So, let's talk about him. We are asked to find the integral from negative 2 pi to 4 pi of f of x dx. And we need to show the computations that lead to our answer. So, I know that f of x is defined as g of x minus the cosine of x over 2. So that's going to just get thrown in. And then what I'm going to do at this point is evaluate them separately by subtracting apart their integrals. So I have from negative 2 pi to 4 pi of g of x dx minus the integral from negative 2 pi to 4 pi of the cosine of x over 2 dx. Okay? Now, I can evaluate this using areas. Okay? So I'm going to go from negative 2 pi to 0. This area right here would be 2 pi by 2 pi divided by 2 because it's a triangle. So this first piece would be 2 pi squared, basically, divided by 2. So that would be 4 pi squared over 2, which is just 2 pi squared. And then this piece on this side has a length of 4 pi and a height of 2 pi. So that would be 4 pi plus 2 pi, times 2 pi all over 2, because I got to divide it by 2, it's a triangle. 4 pi and 2 pi make 8 pi squared, and when I divide that by 2, I'll get 4 pi squared. And so that's how we end up getting this 6 pi squared piece right here, 2 pi squared plus 4 pi squared. Now, the second piece, let me just kind of erase, oh dear. What did we have here? This video may be a little longer than what I was hoping. This is negative 2 pi, and this is the cosine of x over 2 dx. So I have u being x over 2. I have du being 1/2 dx. So I need a 1/2 in there, which means I need to counteract with a minus 2. So I have minus 2 times the integral of the cosine of u du, and that antiderivative is the sine of u, and my u, actually let's go ahead and switch that out, is going to be x over 2 from negative 2 pi to 4 pi. Don't forget we've got our negative 2 hooked on out front. So I have negative 2, the sine of 4 pi over 2. 4 pi over 2 is 2 pi, sine of 2 pi is 0. And then negative 2 pi over 2 is just negative pi, and again the sine of negative pi is also 0. So this is going to wipe out your negative 2, and so that is how we still end up with just 6 pi squared. Yuck. Okay, let's go to part B. Don't worry, part C is the worst part. Okay, part B. It says find all x values on the open interval from negative 2 pi to 4 pi of which f has a critical point. Critical points are where the derivative is equal to 0 and also where the derivative is undefined. So, I need to take f and find his derivative. Well, f is g, which the derivative of g would be g prime, and then the derivative of negative cosine would be positive sine of x over 2, but don't forget, chain on that 1/2. So you have g prime of x plus 1/2 times the sine of x over 2. Okay? Now, wait, it was actually part B that was yucky. G prime. Let's just kind of look at the g prime. G prime is just the derivative of g. So let's go over here and look at this guy. The derivative at this point of g is actually a piecewise function. And my first piece is going to be the slope being a positive 1 over negative 2 to 0. So we have positive 1 over negative 2 pi. I'm just going to put brackets here to 0, but not including 0. And then also my slope here, if we look at this point, my rise and run is 2 and 4. So that would be a slope of negative 1/2. And that would be over 0 to 4 pi. Okay? So I have two different pieces that I need to set this equal to because I'm trying to find where my derivative of f is equal to 0. So I have 0 is equal to g prime of x plus 1/2 times the sine of x over 2. So g prime of x is 1 in the first piece, and it's negative 1/2 in the second piece. So let's just do the first piece here. 1 plus 1/2 times the sine of x over 2 equaling 0. So when I subtract that over, and I'm going to multiply that 2 to the other side. So I have negative 2 is equal to the sine of x over 2. And if you remember, sine is not allowed to equal anything outside of negative 1 to 1. So that's not possible. I also have this situation with negative 1/2. So when I plug that in, I have 0 is equal to negative 1/2 plus 1/2 times the sine of x over 2. I'm going to add that 1/2 over, divide that 1/2 off, and I will end up getting 1 here is equal to the sine of x over 2. And sine is equal to 1 at pi over 2. And so x here, when I multiply my 2 over, would equal just pi. That's not the only thing though, because critical points are also where the derivative is undefined, and you notice that we have a corner right here at that spot, so the derivative is undefined at 0, and it's equal to 0 at pi. Told ya, it was yucky. You got your points here for having the derivative, at least finding the correct derivative for cosine of x over 2. That's a great gimme point right there. For recognizing that you got to find the derivative of g being a piecewise function, and then you get a point for that critical point and a point for that. So if you even miss this part right here, you do still get the point if you got down to the pi. Okay? And then the last part here just talked about a new function, but using the old ones. And it says h of x is the integral from 0 to 3x of g of t dt, and you're asked to find the derivative of h at negative pi over 3. Now, you're asked to find the derivative of an integral, so you realize that this 3x needs to get plopped in, and then you don't forget to chain on that 3x's derivative. So you should have g of 3x, this is the derivative, h prime of x, times the derivative of that upper limit. Please don't forget to do that part. So you have 3 times g of 3x. And then you're asked to put just negative pi over 3 in, so that would be 3 times g of 3 times negative pi over 3. Those 3's cancel right here. So I have g of negative pi. And, oh poo, g of negative pi, g is the function that's shown up above. Negative pi, the derivative, I'm sorry, the value there is pi. So you have pi times this 3, and so that's how we get our 3 pi. So you get a point there, 2 points for having the correct antiderivative or I'm sorry, the correct derivative. So this guy's worth a 2, and your answer is worth another one.